Have you ever wondered if there's more to the universe than meets the eye? Dr. Matej Pavšič, a leading theoretical physicist, has spent his career exploring these very questions. His work dives into fascinating ideas like invisible particles, alternate realities, and even the nature of time. Throughout your career, Dr. Pavšič, you have tackled some of the physics' most mind-bending questions. You have explored the possibility of invisible particles, investigated the idea of the universe existing on a higher dimensional membrane, and even delved into the complex mathematics that helps us describe the universe. Today, we have the privilege of hearing from you, Dr. Pavšič, yourself. You'll share your insights on the fascinating world of theoretical physicists, the challenges and the rewards of scientific exploration, and perhaps even inspire the next generation of curious minds who dream of unraveling the universe's secrets. Thank you so much for taking out your time, sir. And okay, so moving on to the first question. How did the education system help you support your interests? Were your peers and your classmates and your colleagues as curious as you?
Yeah, okay. To answer this question, I must say the following. So before entering school, I was much influenced by three crucial persons: my father and two uncles. My father was a Slovenian poet and writer, much interested in philosophy and science. It was from him that I first heard about the possibility of additional dimensions when he told me that our universe might be closed and embedded into a higher dimension, and that we are like creatures on the surface of an egg. One of my uncles, who was a chemical engineer, explained me, among many other things, the basics of special relativity. The other uncle, who was an electrotechnical engineer, explained me working of simple electronic devices, so that I was playing also with such simple devices. At school, I was much interested and was listening carefully what teachers were talking to us. In gymnasium, we had a professor of mathematics and physics who was so inspiring that five people from his class entered studying physics, and three finished it. At the university, we also had some very inspiring professors. In parallel with the official program, I was also studying additional topics that interested me and researched them in depth on my own. So besides the official program, I was also doing research and explorations already at that time at university. I early discovered already in gymnasium that I had a good intuition regarding theoretical physics. When thinking about the transformations such as translations in space and time, it came to my mind that energy conservation comes from the fact that physical laws do not change with time. This was clear to me without performing any calculations. Later, I found that I had intuitively envisaged the well known Noether theorem about conservation laws. During my university studies, I formulated an extended relativity theory of slower and faster than light particles based on subluminal and superluminal transformations. This transformation link slower and faster than light velocity. My paper was
Right.
not published, but soon I found similar articles by Erasmo Recami. Uh, okay, when working at the Institute Joseph Stefan and thinking, besides others, about the foundations of quantum mechanics, I came to the idea that different possibilities implied by quantum mechanics, by quantum mechanical wave function, are realized in parallel worlds. I was not much surprised when soon later I found an article about Everett's many-world interpretation of quantum mechanics. When researching generalized conformal relativity formulated in 6 dimensions, I rediscovered Kaluza-Klein theory before I was being aware of it. So it's very interesting that I discovered something, but later I found, okay, it was not me who was the first. But anyway, I said, this is good sign that perhaps sometime in future I will discover something that was not yet be discovered by anybody else. Okay, yeah.
I find that answer very inspiring, sir. Actually, once a similar thing happened to me. By mistake, I ended up deriving the Schwarzschild's radius and found the ratio between a black hole's mass and the radius and how it was always constant. And then later I realized that it was already discovered.
Yeah. Okay, yeah, very good.
So, moving on, how has
Yes.
your daily work schedule changed over the years and what is it like at the moment? So, what does a day in your life look like?
Yeah. Uh, First, when coming to the institute, I had to work on the problems regarding, for instance, the analysis of the Doppler shift measurement in nuclear physics. But gradually, I started to work more and more on the topics of my own choice. After master degree, I spent 1 year at the Institute of Theoretical Physics in Catania, Italy, collaborating with Erasmo Recami. We wrote many papers on tachyons, conformal relativity, cosmology, and so on. We also collaborated with the renowned professor Piero Caldirola from Milano. We visited him once at Milano, and then came back to Catania and so on. Okay, when
Hmm.
back to Ljubljana, I defended my PhD thesis on conformal relativity and continued research in fundamental theoretical physics. After some time, I started to collaborate with the renowned physicist Asim Omar Barut from the University of Colorado on spinning particles.
Hmm.
In 93 to 94, I was a visiting professor at the Institute of Applied Mathematics in Campinas, in Brazil, collaborating with Valdir Rodriguez Jr. on Clifford Algebra. Okay. I attended many conferences in various places around the world. Okay, if you are talking about today's schedule, now I'm officially retired, not still connected with the institute. So I mostly work at home. Um, yeah, so I'm now more or less free. Okay.
Okay, so moving on to more technical concepts now.
Yes.
How would you, so your entire study and research on physics concerns various dimensions along with extra superluminal particles and such. So, how would you define a physical dimension?
Look, if one considers a physical object, one can approximate it by a single point. If looked from very far, it indeed appears as a point. Just recall the picture of the Earth taken by, I think it was Pioneer probe, space probe Pioneer, when leaving the
Yes.
solar system. The Earth was just a point. Also, stars are just bright points in the sky. Their position on the celestial sphere are given by two numbers. Their distance from the Earth is the third number. So to determine the position of any object requires three numbers. Those numbers are associated with three independent spatial dimensions. Dimensionality of a space is given by the number of parameters necessary to determine the position of object approximated as point.
Okay. So basically, how we can go from one object to another in terms of vectors, I think uh, that would be the dimensionality, right?
Mhm.
So being, you say that there are more dimensions than three, right? And
Yes.
we are just three-dimensional beings.
Mhm.
So how do you think you would find evidence for higher dimensions from your own or a three-dimensional being's reference point?
Yeah. Uh, an evidence for higher dimension would be if the description of certain objects or processes would be much simpler if considered as projections from higher dimensions. So let me illustrate this on the example of a cubic lattice projected onto the plane. So sharing the first slide, do you see the slide? Uh, do you see a slide?
Yes, sir, it's visible.
Is visible, yes, very nice. So look, here you see uh, what we actually see on this picture are intricate structures on two-dimensional plane, which is just this two-dimensional slide. But our brain interprets them as cubic grid in three dimensions, viewed from different perspectives. In the plane, the structures are complicated, while in 3D, there is only one simple picture, namely a simple structure, namely
Yes, sir.
a cube. Now, suppose now that three-dimensional objects are complicated, intricate structures, their mathematical description is difficult and tedious. Then, after a thorough study of such objects, we discover that they can all be described as different projections of a simple structure existed in a higher dimensional space, so projected onto our three-dimensional space. This would indicate the presence of higher dimensions. Uh, because a theory that takes into account higher dimensions would be much simpler than a theory that takes into account only three dimensions. In fact, such structures actually exist. When they were discovered, they did not fit into the conventional theory of crystals. Therefore, they were called quasi-crystals. In this slide, there are some examples of quasi-crystals. Uh, and further studies revealed that quasi-crystals are projections of six-dimensional or higher-dimensional crystals onto the three-dimensional plane, three-dimensional space. So here is an article where the scientists were considering how eight-dimensional cubic lattice can be projected in different ways. Or this is just for illustration. I don't want to talk too much about this. Now, we could say that the involvement of higher dimensions in the theoretical description of quasi-crystals is only a convenient mathematical tool, while higher dimensions do not really exist. But I think that quasi-crystals are evidence for higher dimensions. But since the atoms of quasi-crystals are within our three-dimensional space, so therefore, the higher dimensional space must be a sort of configuration space of objects in three-dimensional space. So somehow, so of course, configuration space is higher dimension, and a possible configuration space is Clifford space, a 16-dimensional space that I will mention later. So let me stop at this point about this.
Okay, so moving on, I think I got a basic understanding of what a dimension is and how we speculate that there are more dimensions using mathematical frameworks. So going on to the next topic, this is about one of my most interesting topics. Do you think that negative energy density fields exist? And if so, how would they contradict the conservation of energy? And because we have both positive and negative fields, if this is true, then would it be sensible or possible to assume that the net energy of the universe equals to zero?
Oh, yeah. Look, in several works of mine, I have considered negative energies in various contexts. Conventionally, whenever in a theory or in a model there occur negative energy, it is taken for granted that such theory or model is physically unviable, impossible, not good for physics. Why? Because it implies instabilities and runaway behavior. For instance, if we consider an oscillator with 2 degrees of freedom, one with positive and the other one with negative kinetic energy, then the vast majority of physicists think that in the presence of an interaction, such system is necessarily unstable. I have found that this is not the case for physically realistic interactions given by the potentials that are bounded from below and from above. If the potential is not bounded, then the system exhibits runaway behavior. An example of such unbounded potential is here. Let me see if I could go to the next slide. I don't know why. No, I must click here. No. So, yeah, I must go. So this is now example of an unbounded potential. Mathematical, this is just the difference of the square of the degrees of freedom, x squared minus x squared. This is the potential, and this is the total Lagrangian function from which we derive the equations of motion. Now, for this potential, it turns out straightforwardly that a solution is or in general an ellipse. Why? Because the minus sign is here in the kinetic energy and also in front of this epsilon. So nothing changes in the equations of motion. Yes, well, everybody knows this is okay. But if we have a coupling term, a term in the potential that couples x and y, for instance, if we have this potential, with the cubic term, then, so this picture is like this one. It goes into infinity here and down into infinity. Then the solution is no longer an ellipse, closed surface, but it started exhibit runaway behavior. First like ellipse, and then and it goes to infinity. So this is the trajectory in the xy space. And the kinetic energy, for instance, for the x component, x dot square goes to infinity. It increases. So on this graph, it is not visible that these are oscillations. These are oscillations whose amplitude is higher and higher and higher and higher, goes to infinity. But the total energy given by the kinetic energy plus potential energy remains constant. This is result of numerical calculations for such system. So this system is unstable. This is generally accepted wisdom. Oh, so negative energy has no sense. But what if we consider now a bounded potential? So the same potential as here, damped with certain exponential functions, so that this cannot grow into infinity, but is damped. Is damped. Yeah.
Okay.
In this way. For instance, then these peaks do not go into infinity, but is damped. And what then happens with the solution? The solution for certain time period, it increases in this direction, but then suddenly it starts to increase into this direction. So the trajectory fills bounded region of x, y space. And the kinetic energy envelope, the maximum of kinetic energy, increases, and then goes down, and then again increases and goes down, and so on. So this was for certain initial velocity. But if we suitably increase the initial velocity, then we have for certain time period this increase, but then it does not go down, but it escapes from the potential region with constant velocity. So we have this. Another possible case is this one, when we have this wavy surface potential. This potential is wavy surface, and for sufficiently small velocity, the system oscillates within a bounded region. So it performs this interesting trajectory, and velocity is just oscillating and never goes to infinity. If we start with higher velocity, then the system oscillates for some time within this region, but then it escapes with constant velocity and again oscillates. So we have this interesting trajectory when the particle, the point wanders around the xy space. And the velocity is always bounded. So the system is stable in the sense that velocity or energy never escapes into infinity.
That's a good.
See what I have here. Yeah, so this and this. So now concerning your question, yes, negative energy density fields do exist, at least theoretically, are possible, and they do not contradict the conservation of energy. The net energy of the universe can be equal to zero. According to the general opinion, such field would instantaneously decay into infinitely many positive and negative energy states. And thus, such system would be unphysical because it would decay instantly. But I think that it is not unphysical, just the opposite. It could be an explanation for Big Bang. I will later explain in some more detail why and how.
Okay, sir. That's a really interesting thing to know, because like always thinking of negative energy, me personally, I have been associating it to negative mass and messing up the whole of the universe according to that confusion, I guess, or perception. So your research is also based on gravity, right? And So, what is your opinion on ultra hyperbolic spaces and higher derivative gravity? So, first of all, could you define these terms and then move on?
Ultra-hyperbolic spaces have indefinite signature. So it means that the signature has plus, plus, and minus, minus signs. And thus implies positive and negative kinetic energies. So if you construct Lagrangian function in such spaces, it has the terms with positive and terms with negative kinetic energy. And what is even also very bad for physicists in general, that there is no separation between the space-like and time-like region. Because a particle from the space-like or from the time-like region can escape in this six-dimensional space or ultra-hyperbolic space into the velocity that are higher from the velocity of light. There is no such strict limit as it is light speed, because in four-dimensional space-time, particle, when accelerated, sooner or later, not sooner, never, but it approaches infinite energy and cannot pass velocity of light. But in hyperbolic space of higher dimension, ultra-hyperbolic space, it can go around and go to the higher and higher speed, superluminous speed.
Right.
Okay. But this all is considered as physically unviable because the occurrence of negative energy and causes instabilities, and tachyons are problematic because of causality violation. Usually people say tachyons violate causality. Moreover, wave equations in such spaces are considered as problematic because the Cauchy problem is not well posed. So what does it mean? This means that one cannot define initial conditions on a hypersurface and then calculate the future behavior of the field. In my papers, I have shown why ultra-hyperbolic spaces are physically viable within a properly formulated theory. Higher derivative gravity contains negative energies, therefore they are considered as problematic. But the studies of simple models such as the oscillator with positive and negative energy degrees of freedom that I showed just a few minutes ago, show that physically realistic models in which potential is bounded are stable. In the case of infinite degrees of freedom, okay, with the harmonic oscillator, I have only x and y degrees of freedom. But in the case of field, there are many, 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 many degrees of freedom, infinitely many. So in the case of infinite number of degrees of freedom, which is such as field theory, higher derivative gravity, the expected instantaneous vacuum decay is also not a problem if considered from a proper perspective, namely from the point of view of the observer. Namely, vacuum decay is instantaneous for an observer outside the system described by the higher derivative theory. But it is not applicable if such a theory is the theory describing our universe. Every conceivable observer is a part of our universe. The inside observer is coupled to the particles in the universe, so that thus at least implicitly measures their momentum because it is coupled. For such an observer, Vacuum does not decay instantaneously, and yet it decays, and it causes Big Bang. So this was elaborated in some more detail in my published works. So there should be said a lot of things before making these things clear. But the idea is that maybe in physics they usually say that if you don't measure the final momenta, then the phase space is huge. And in the case of field theory, the phase space is very, very big, so huge that decay happens instantaneously. But this is because the observer does not measure momenta, but the observer inside our universe is coupled to measure. So it must, by definition, measure only a certain range of momenta, or let me say simply, a certain momenta, and therefore there is no instantaneous decay. And yet there can be cases in which, nevertheless, the observer does not measure very well momenta, and so we can still have a sort of instantaneous decay in certain region of parameters. This is explained in my papers. So then we can have Big Bang. Let me stop here because it is starting to be too complicated. But if somebody is interested, if they go to my works, they will see how it is explained. And some people found it interesting and cited my explanation in their works.
Sir, I went through the paper you're talking about, and I actually was not able to understand the outside and the inside universe part. Like the observer being outside the universe and not being able to notice the momentum, while the object being inside the universe and figuring out that not everything is instantaneous. The decay, I mean. I was not able to understand this, but I think it's much clearer to me now. So,
have you heard about the watchdog effect of quantum mechanics? If you leave the system's evolution free, the particle or the system degree of freedom is more and more uncertain. But if immediately after that you measure it, it is frozen. You will again measure practically the same quantity. And if you continuously measure, the quantity will stay frozen. So this is related to watchdog effect. What is, you are still very young. You have not yet in university.
yeah, I'm in high school, sir, 10th grade.
I understand it is necessary to study more. I'm trying to explain these very complicated things for young people, very interesting people.
Do your works have concerned string theories for various speculations and assumptions? So, do you believe in the string theory, particularly the brain theory of string theory?
Theories are not something to be believed in. I think that brains are useful mathematical objects for description of physical objects. But the real physical objects are not exactly brains, as they are also not exactly point particles. Such considerations lead to the concept of Clifford space, the space of oriented brains. So let me start the illustration with this. Now again, problem because somehow the slide is frozen. How to then? The problem is that now now I have it. Yeah. But I cannot move it so that I would see him. I see now only part of the slide. Very tricky. No, doesn't matter. So, I would like, so do you see the entire slide?
Sir, I think there's a greenish image on the right side that's blocked.
Yeah, now I understand what the problem. Yeah. Do you see the slide?
Sir, there's a green image thing on the side that has been blocked on the right side.
Look, here we have a red line, closed line, which represent a closed string. Do you see it?
Yes, sir.
Okay. Now, so this is an object, closed string. At first approximation, we can describe it just by considering its center of mass, given by center of mass coordinates. At the next approximation, we can consider the holographic projections of this oriented area onto the coordinate plane. So these projections are x1, 2, 3, x, and so on.
Yes.
And if we go, if we consider even the object in more detail, we could discover that actually it is not a string, but a brain, two brain, and it is described by the volume coordinate x1 to 3, because now we have volume enclosed by this thing, and so on. We arrive at the concept of the set of coordinates which are center of mass, oriented areas, oriented volumes, and oriented four volumes if we are in space-time. And so we arrive at 16, altogether we have 16-dimensional such objects. And this is called Clifford space because, okay, I will not go into detail why Clifford space. The basis of this space is the basis of Clifford algebra. But this is perhaps too complicated at this level of presentation. No, let me now say, string theory is something else. I was not working on that theory. I think that one can avoid all the difficulties related to the compactification of higher dimensional spaces necessary for consistent formulation of string theory by formulating string theory in six-dimensional Clifford space. Clifford space could also be the arena for description of quasi-crystals as higher dimensional crystals. Yeah, look, this is sort of configuration space because we have configuration which is just this form, like closed string, which when you look at it more closely is in fact closed brain and so on. And this is a sort of configuration space. But all those objects are still in our space-time and yet described abstractly, mathematically as higher dimensional object. And now I'm thinking how you could envisage crystals in such space that would look quasi-crystals in our three-dimensional space. I think that some people were also considering the idea that quasi-crystals has something to do with Clifford algebra and Clifford space, but I have no definite solution concerning this issue. So let me stop at this point about this.
So when I was reading your papers, I had the same doubt on what Clifford algebra is. From what I got it, because like understanding it on Google was very hard for me, so I had to ask ChatGPT. And from what I understood, Clifford algebra is basically, or Clifford space is basically a plane where we can kind of do maths for translations and rotations. Is that correct?
Yes. But we are certain community which are considering Clifford algebra even further, not just as a tool for describing rotations, but there are much more things within Clifford algebra than usually considered by many people. For instance, okay. If you look my paper, you will see in what respect they are just along the usual line, in what respect they go beyond the usual concept. Because usually people don't consider the concept of Clifford space. And I don't know if this is too complicated for this level of audience, but Clifford space is a tangent space to a manifold. Clifford space is a manifold whose tangent space is Clifford algebra. But okay, let us leave this for future. Okay.
Okay. So your research on brain worlds suggests that there might be more to the universe than we can observe, such as hidden curled up dimensions. So does this concept of a multiverse make you think about the possibility of infinite realities or alternate versions of ourselves?
Uh, yes. Uh, an attractive idea is that, so let me start with this attractive idea that our space-time is a four-dimensional surface, a brain embedded in a higher dimensional space.
Hmm.
So our brain, of course, I cannot write or design here, plot here a
Yeah.
four-dimensional surface, so I plot here only two-dimensional surface. This one-dimensional line is our free space, this is time, and altogether this strips a four-dimensional surface represented here as two-dimensional surface. So this, according to the brain world scenario, our universe is a brain embedded in a higher dimensional space. Matter can be given by intersections with other brains in this higher dimensional space, or with self-intersections of our brain. In both cases, we get matter, for instance, in this case, as a word line on our four-dimensional brain surface. And here also, but the surfaces can be little, the intersection could be more complicated. Instead of word line, it can be worksheet or word volume,
Yes.
and so on. So matter is given by intersections with other brains or self-intersections.
Okay.
In my book, I have elaborated, for instance, that in the case of a word line, this word line satisfies the geodetic equation on this brain, a word sheet, word volume on our space-time surface. And okay, let me now say the following. Alternative brains
Mhm.
represent alternative words. Okay, let me go to the next slide. So these are alternative brains, now represented here just as lines to visualize it. So alternative brains, or this is one brain, but they can be alternative. When you look from this side, you see this many different possible brains. But quantum mechanically, there is no definite brain, but a wave packet of brain represented schematically on this figure. So wave packet embraces many possible words, but it is localized so that the average of all those alternative words, average, is an effective space-time, V4. So wave packet here is represented by this shape, which bounds the possible range of brains. So brains are packed here inside but not outside, or very rare branes are outside this envelope here. So on average, we have this average space-time surface before. Additionally, the wave packet can be more sharply localized within a space-like region P. With the evolution of the wave packet, the region P moves along D4. Such a wave packet describes an observer who is not experiences the entire space-time in all details at once, but experiences it step by step within a sharply localized region. Such wave packet does describe both the presentism of relativity, the block universe, because this wave packet is still localized around certain space-time, yes, because, okay, but it is more sharply localized in this region, and thus describes the becoming, subjectively experienced by observer. Becoming is technical term for our experiencing of flow of time. In this way, we have a unification of the concept of flow of time and block universe. Block is this one. So, but okay, this region of sharp localization can be even more sharply localized so that it is not localized on the entire space-like surface, but only in certain part of space-like surface. For instance, around a certain observer observing the universe. So he's really sharply aware only of certain surrounding and certain time interval during his evolution or progression along space-time.
Yes.
Okay, I think that this is what I wish to say about this question at the moment.
Okay, so moving on, would
Yeah.
space be able to exhibit properties that can only be explained with an infinite number of branes? Or, in other words, can strings kind of bend or maybe vibrate or have freedom in an infinite number of branes?
Look, branes can be considered as infinite dimensional object, as points in an infinite dimensional space, the so-called membrane space, brain space. A complete description of a brain requires uncountably infinite number of coordinates, namely the brain's embedding functions. In brain space, we can introduce metric. The usual brains, so let me see, yeah, the usual brains live in a brain space of a special, non-trivial metric. We can consider a theory in which the brain space is the brain space metric is not fixed but dynamical, like the metric in general relativity is dynamical, given by Einstein's equation. Now we have generalization of these concepts to this higher dimensional brain space. The usual brains are particular solutions of such general theory with the dynamical metric. In particular, the metric can be just a simple metric of an infinite dimensional flat space. So flat space has metric 1, 1, 1, 1, 1, or eventually 1, 1, 1, minus 1, minus 1 on the diagonal. So let me illustrate the concept for the so-called flat string. So the worksheet of a flat string is an infinite set of straight word lines. I'm interested. Do you see the movement of my cursor or not?
Yes, sir.
You see.
Yeah.
Okay, so you see that now I'm circling this and now I'm circling this. Yeah, nice. So these are straight word lines. Bunch, infinitely densely packed bunch of word lines forms a word sheet, swept by a string.
Right.
Yeah. Okay. So this was very simple case, but we can consider more complicated cases. For instance, like this one here,
Ah,
depending on the initial conditions, we have many interesting configurations of flat string. What is typical for flat string? That that word lines of particle or forming them are straight line. Or whatever complicated, however complicated the structure is, the lines are always straight. You can
hmm.
always find the set of straight lines. This is flat string. Now, yeah, but what about the cases when um, the metric of brain space is not is not flat? So here are
Hmm.
examples of the so-called curved. Okay, curved string. This is very bad language because what is curved is the string brain space or string
Yeah.
space in which they live. Infinite dimensional space is curved, and then
Hmm.
we have such structure. Now these word lines are no longer straight lines, are can be curved, and they perform very interesting structures. Uh,
Hmm.
so these are. I will not give you now formulas how is the metric because it would be too much at this level of understanding of the subject, attended, our audience, the
Yeah.
target audience. Okay, now here are examples of, of the usual strings. Example of special kind of curved string, the Nambu-Goto strings. Typical
Hmm.
for that strings that by suitably choosing boundary condition, the worksheet cannot self-intersect. Here's it self-intersected, but in Nambu-Goto strings, it does not self-intersect. So you have
Right.
this behavior. So this is string, it goes, so here is in this direction is time, it's not, and it goes progress here, or it can, so this represent circulating strings. You see, orientation of this string is this here, is all, at each moment of this x naught, is time, is different.
Yeah.
Okay, uh, so as infinitely many closely packed point particles can form strings, so infinitely many closely packed strings can form membranes, tubranes, and so on. Thus, infinitely many closely packed, let me say, p minus 1 branes can form p branes, and each of the p minus 1 branes is a set of p minus 2 branes,
Hmm.
and so on. We conclude that within these general setups, starting with point particles, we can form arbitrary branes. Hence, my theory suggests that a properly explained property or object explained by infinite number of branes can also be explained by infinitely many strings. Um,
Hmm.
the realization realization that one must start a brain theory in flat brain space and then extend it to curved brain space is a crucial step towards brain quantization. Namely, a flat brain can be straightforwardly quantized as a bunch of point particles. If we take suitable interactions between the quantum fields, we obtain as an expectation value the classical Nambu-Goto brain or other kinds of brains. because we have now dynamical metric. So this dynamical metric in classical brain space can somehow be obtained as an effective metric starting from the bunch of quantum fields and introducing suitable interactions among them. So this could be one step towards quantum gravity within the brain world scenario. We have thus found how to quantize brains. How? We are flat brains. Non-flat brains are then objects of effective classical theory.
Yes, sir.
Effective classical theory that arises from the underlying quantum field theory of many interacting fields. This is also a possible road to quantum gravity within a brain world scenario.
Right. So that's all the questions I had, sir. However, I think that there would be many more questions that I would have, and the community also has, that we would love to be answers by you in a future episode, I guess.
Yes?
And I would like to thank you so much for taking your time to inspire all of us. And me personally, I want to work exactly in theoretical physicists in the field of theoretical physics. But but I noticed this in various people. When I tell them about theoretical physics, the first thing that comes in their mind is that physics was meant to describe reality, and that theoretical physics should technically not exist. But talking to you made me feel like it is possible, and there's much to discover that I would like to work upon, and maybe solve the problem of quantum gravity one day.
Yeah. Unless artificial intelligence will not be first to solve it. Okay,
Yeah.
but maybe artificial intelligence is progressing so rapidly that perhaps it would understand all these complicated theoretical subject much
Hmm.
better than us. Okay, but still, until then, we must take effort to study.
I think we still have a chance.
Yeah. I'm very glad. So, how old are you? I read that you have 15 years. So, is this true? Still true or not?
Yeah, I am 15-year-old, sir.
Oh, I'm absolutely fascinated how far you understand such concept, how much you studied. And okay, I wish you a lot of success in your later career. Okay, so I look forward to record further post podcast because you post so many interesting questions.
Conversation with Dr. Matej Pavšič was a captivating exploration of the universe's mysteries. His passion for theoretical physics, particularly the mind-bending ideas of alternate realities and invisible particles, was truly inspiring. Through the conversation, we gained a deeper appreciation for physical dimensions, energy fields, and the brain instinct theory. Dr. Pavšič's dedication to unraveling the universe's secret is a testament to the power of human curiosity. For those who want to delve deeper into the fascinating world of theoretical physics, Dr. Pavšič has authored two insightful books. The Landscape of Theoretical Physics, a global view, promises a comprehensive exploration of the field. And the other book is Stumbling Blocks Against the Unification, which is on some persistent misconception is physics, tackles common roadblocks in our understanding of the universe. A sincere thank you to Dr. Pavšič for sharing his knowledge and enthusiasm. There's much more to learn from Dr. Matej, so you will be seeing him again soon. This is Kush, signing off.